Okay, good morning. So we're going to talk today, or start talking today, about improper integrals. And although improper integrals get smushed together into a single section, this is really multiple topics that are only kind of related to each other. Let's start by looking at, our textbook breaks this down into case 1 and case 2. We'll start by looking at case 1, which is something like this. The integral from 0 to 1 of 1 divided by x. So how does this differ from the integrals we've looked at so far?
Well, it starts at an undefined spot.
It starts at an undefined spot. We have 1 divided by x, and we're starting at 0, and 1 divided by 0 is not defined. And this would show up if you then try to compute this integral using the fundamental theorem of calculus. When you, let me start my calculator loading up, but I'll just say that if you plug the natural log of 0 into your calculator, you're going to get an error. Just as if you try to divide by 0 or take the square root of a negative number. So this is undefined. And if you think of the integral of a positive function as the area under a curve, you're trying to take the area of an infinite region. You've got your curve. It looks something like this. This region just extends up to infinity. It gets very thin as y gets big. But this is an infinite region, so it makes an intuitive amount of sense that we can't talk about the area under this curve on this interval, except that that intuition breaks down in some cases. This function has the exact same issue as the last function. If we let x be 0, we get a division by 0 error. Just like with the last function, this region extends infinitely upwards. But we want to say that this integral is finite, that even though the region extends infinitely upwards, it has a finite area. This integral, on the other hand, is infinite. The region extends infinitely upwards, and it has an infinite area. So what's the difference between these cases? How do we define the area under a curve in this situation? So let's talk about how we might define the area under a curve. And as is usually the case with calculus, I mean, if you asked me to summarize what calculus is, it's the process of making an approximation, then making the approximation better using a limit. So let's take a look as soon as my internet wants to cooperate and I can get to Desmos. Let's take a look at the area under this curve on the interval from 0 to 1. And let me mess around with these graph settings so that the stuff we actually care about is made more prominent. So this is a region that extends infinitely upwards, but which I'm claiming it makes sense to think of as being finite. How might we approximate this area? If we're willing to accept that this area exists, how could we approximate it? So this 0 is the problem. Because 1 divided by the square root of x would give you an error. But you can have a small value here. I mean, you could have a 0.1. And this is not quite the area we're looking for, but I mean, it's got a lot in common with the area we're looking for. If we compare this, the area we can find, with this, the area we actually want to find, we see that it has this entire shaded region in common. But we're also missing a bunch of area. All this stuff up here, this pink region in here, this is area that we want and don't have. So how could we make our approximation better?
You make that value smaller.
Keep making that value smaller. Maybe I made that a little too small. Now we can't see the difference. So when I go from 0.1 to 0.05, you see we get part of this region that we didn't have before. If I go to 0.005, as far as we can tell, these regions are now the same. And I mean, they aren't. If we went to the graph settings and we let x start at 0 and go to 0.1, we could now see a difference, but to see this difference, we had to zoom in. And if I made X even smaller, the difference becomes even more significant. I'm not even sure if most of you will see this very thin band of pink over here that represents the difference between the area we can find. And again, finding this area is simple. We can use the fundamental theorem. There aren't any issues here. And as this lower limit gets smaller and smaller, this area, which we can find, ought to be getting closer and closer to this area, which we want to find. So let's try to formalize that. Let's look for the moment at the specific case wherein we're taking the integral from a to b of a function, and this a is a vertical asymptote. So this function isn't defined at A. And I mean, it's not defined at A in this specific way. It's not defined at A because we get a division by zero error at A. Then formalizing what we were just doing in terms of a limit, we'll replace A with some other number, and we'll see what happens as that other number gets closer and closer to A. That's a limit. And there's our definition of the integral, the definite integral in this case. And fortunately, you know that limits can be hard to work with, but we're not going to have to use any fancy limit finding tricks. Let's see how this works out in practice. And let's use the two examples we've put on the board. So we'll start with this. And in mathematics, I mean, I know it can be picky seeming. Sometimes it is picky, but we really do want you to use correct notation and correct procedure. So we're taking, we don't have some abstract A there. We have zero specifically. We have this integral defined to be this limit. I mean, a little more properly speaking, it's the right-hand limit. We're starting above zero and going down. I mean, the way we're going to find an integral like this is we're going to ignore the limit for a moment. We're going to take that definite integral, and then we're going to see what happens to the definite integral as n goes to zero. So this is x to the negative 1/2. So we bump the power up by 1. We divide by the new power. We're evaluating from 1 to n, or from n to 1, I should say. So we plug 1 in there, we get 2. We plug n in there, we get 2 times n to the 1/2. And what I said earlier about not needing a bunch of, fancy limit finding tricks, it's because we work with continuous functions. We can just plug 0 in there. And we get a finite number. Which is, I don't know if you feel this way, but it could be thought to be quite unintuitive, because again, this region we are looking at does not have finite bounds. It keeps going up and up and up, and it never stops. But it gets so thin up here that the area somehow manages to be finite, in spite of the fact that we probably can't even see it anymore. But let's see. Come on, Desmos, work with me. Point. I am sitting in an inconvenient place. There. So we see that, we go up to 176 or whatever. I mean, we still have area under the curve. It's just, again, that this area, I mean, I intentionally magnified it to look bigger than it is. We've got x values here of like 0.000002. So by becoming extremely thin, this area manages to be finite, even though it has no upper bound. And that's pretty remarkable in a way. And it therefore shouldn't be super surprising that not every problem we look at with a vertical asymptote is going to turn out this way. Here is an infinite region with an infinite area. And to see that, I mean, we start by recognizing that this is an improper integral. If we let x be 0, we get a division by 0 error. So we define this as a limit. And then we compute this integral using the fundamental theorem of calculus. We, for the moment, are not going to worry about that limit. We'll just take the integral and see what happens. And because I already put this integral on the board, I won't try to wring drama out of this. We integrate 1 over x, we get the natural logarithm. Get the natural log of 1 minus the natural log of n. No problem here, everything is perfectly defined. But we're assuming here that n is a positive number. Again, after lecturing everyone about, notation and stuff, I sometimes get kind of sloppy and just write limit. We're really approaching this limit from above. We're assuming that n is positive. The natural log of 1 minus the natural log of n. And this might not be totally obvious because we might not have a great deal of intuition about the natural log. I mean, you see it sort of at the end of a college algebra course. But I mean, if we plug 0 in here, we don't get a number. I think I got this calculator up. The natural log of 1 minus the natural log of 0. We get a division by 0 error. This limit does not exist. And I mean, we could also look at this graphically. Like we could go to Desmos and we could say, hey, Desmos, we want to look at the natural log of 1 minus the natural log of n. And Desmos is going to be difficult. I was expecting it to create a slider for me so that I could let n approach 0. Instead, it's being inscrutable. Create a slider, Desmos. Why are you being like this? Okay, here we go. So we can see what happens as we approach 0. To be clear, there's nothing in the graph. I'm looking at this number up here, which is telling you what this subtraction is. And it's just going up. And it may not look like it's going up super fast, but it's gone up from 0.8 to 1 to 2 to 3 to 4. It just goes up to infinity as s approaches 0. And if I increase the step size, I could maybe do a little okay, increasing the step size didn't help. But another way of seeing this would be graphical. Maybe that's actually the most natural way to do it. What happens to the natural log of 1 minus the natural log of n? As n approaches 0, well, here's what the curve looks like. As n approaches 0, we are jumping up and we're getting some pretty extreme rounding error here. I'm not sure why. We somehow can't get closer to 0 than this. But if we look at the graph, we can see this is going to infinity. So sorry about my little fight with technology. I love it, but sometimes I'm frustrated with it, as I suppose is a pretty common experience. Anyway, this limit doesn't exist. So this integral does not exist. If an improper integral, and what we just saw, where one of the limits of integration gives a division by 0 error, that's our first example of an improper integral. If an improper integral exists, I mean, that is to say, we take the limit and we get a finite number, we say it converges. Which is maybe a slightly weird in isolation. I mean, we're asking whether an area is finite or infinite. The word converges doesn't really seem germane here, but we're borrowing this word from the limit. We talked about a limit converging or diverging. An improper integral is defined in terms of a limit. So we talk about an improper integral converging or diverging. I guess if we try to take this improper integral and the limit does not exist, then probably pretty much what we'd expect. We say that the improper integral diverges. So an improper integral can converge or diverge. It can be finite, it can be infinite. Sure. The integral from 0 to 2 of the natural log of x dx. So this is an improper integral. It's an improper integral for the same reason that the last two integrals were improper. There is a vertical asymptote at 0. It's not, I mean, we normally think of vertical asymptotes as coming from division by 0. There is no division by 0 here. Nevertheless, if we remind ourselves what the natural log looks like, there is this vertical asymptote. So the natural logarithm, well, first of all, let me rewrite it. The three examples we've done have all had 0 as the lower limit. We can do an example with a different number. Let me make sure I'm sharing what I want to share. I think I am. So we'll take this limit and see what happens. And this is kind of a tricksy limit. If you remember yesterday, I took a limit and I took an integral, and then Wolfram alpha gave an exact value, and it was like, oh yeah, I know how to do this. It's the curse of calculus 2 that there are these tricks that just work once or twice, but somehow you're still expected to know them. The natural log of x is taken by parts, even though there is no product. The trick is to think, well, we don't have a product written down, but we can think of it as 1 times the natural log. Then will that u be the natural log? D of e be 1. Ordinarily, we'd like the function not to become worse when we integrate, when we're doing parts, but it's going to be compensated by the fact that the derivative of the natural log is so much nicer than the natural log. U times v minus the integral of v du. I guess if I'm ever going to scold people for not using proper notation, I'd better put that dx in there. So x, the natural log of x, minus the integral of 1 is x, the natural log of x minus x. And then, because I'm framing this as an indefinite integral, I'll write down the limits of integration. Up here, we are running out of space. Let me write here the limit as n goes to 0. So we have our indefinite integral. We plug in the limits of integration. 2 times the natural log of 2 minus 2 minus n times the natural log of n minus n. And we're asking what happens as n goes to 0. Well, as n goes to 0, It's actually not totally clear what happens. I'm going to just use Desmos, rather than the alternative, which is to somehow rewrite this as a quotient and then hit it with L'Hopital's rule. The reason I say that I don't think it's clear what's happening is that as n goes to zero, this goes to zero, and 0 times a number is 0. But also as n goes to 0, this goes to infinity, and infinity times a number is infinity. So those two things are fighting. That n is trying to make this be 0, that infinity is trying to make this be infinity. And so I've learned my lesson. I'm not going to mess around with the counter, the slider. I'm going to just look at 2 ln 2 minus 2. I think that Desmos is assuming we have parentheses there, but I'll put them in to be sure. Minus x ln x minus x, or we can even, if we write the y equals here, we can use the letters. Okay, and this appears to be finite. This appears to be going to, well, it's hard to say exactly. Negative 0.515, negative 0.549, negative 0.572. Somewhere around negative 0.56. I'm gonna be honest, I thought this integral was gonna diverge. I didn't really have a plan for if it turned out to converge. Let's just approximate that as negative 0.56. And we shouldn't, of course, forget, oh no, I'm wrong. On Desmos, it's not just this that's negative 0.56. It's this whole thing. Not quite what I was expecting, but we'll leave it be for now. I can double check my work after class. There's nothing, I mean, in the 3 cases I looked at, we had 0 as the lower limit. There's nothing special. I mean, I won't go through this problem in depth, but if we had something like that, it would be the limit as n approaches 5 of the integral from n to 7 of 1 over x minus 5 dx. I said that I wasn't going to do this in detail, but actually doing this is like a 2-minute problem. This integral ends up being pretty straightforward. It's a U substitution. U is x minus 5. But we wind up with this. And then once again, what happens as n approaches 5 is that this thing inside the parentheses is approaching 0. The natural logarithm of 0 is infinite. I mean, that's an extremely slipshod way of saying it, but we go to negative infinity as we approach 0. Then the natural log of 2 is some finite number. A finite number minus negative infinity is infinity. This whole thing does not exist. Questions so far? Then there are a few variations of this thing that we can look at. The first variation I'll do today because it's very simple and 9 minutes seems about right for it. I shouldn't say, I mean, when I say something simple, what I'm really saying is that it's very similar to the case we were just looking at. Whether that means it's simple or not, I don't know. But the integral from 0 to 5 of 1 over x minus 5 dx. Well, now we have a division by 0 error and a vertical asymptote, but it's happening up on the top instead of down below. And you can probably imagine 1 divided by x minus 5, we're looking at values between 0 and positive 5. So in terms of this is negative, so we're looking at the area. Let's see, we're looking at the area above the curve. Does this area exist? Well, you can probably imagine what we're going to do. 5 gives us a division by 0 error, but 4.9 doesn't, and 4.99 doesn't, and 4.999 doesn't. So we can let this upper value get closer and closer to 5. And this is then going to be the same idea. We're going to take a limit. It's just that the limit is going to be at the top instead of the bottom. All right, I kind of shot through this on the previous slide, but let's now go through this in slightly more detail. Well, let's just look at the indefinite integral for a moment. So if you do enough examples, you could perhaps just do this in your head. U substitution where du equals dx is the nicest U substitution. It just very cleanly lets us go to something we can integrate. So this, if we now attach limits to this, limits of integration, I should say. We're not yet taking the limit as n approaches 5. We get the natural log of n minus 5 minus the natural log absolute values to the rescue here. The natural log of -5 wouldn't be defined, but because of that absolute value, everything is still okay. I'm going to go to another frame for space, but we're now taking the limit as n approaches 5. Of that. Let me just squeeze it in there and then let's give ourselves some space to work. Natural log of n minus 5 minus the natural log of 5. So in practice, I've been trying to be very, or at least semi-formal. I mean, I've been looking at a limit like this and, I've been going to Desmos or whatever. In practice, 99 times out of 100, if you do all this work and you plug this number in, and you plug this into your calculator, and your calculator spits an error message back at you, that means the limit doesn't exist. And this limit doesn't exist, and this integral diverges. I do want students, again, even if it seems picky to you, we do things for a reason. Math is a place where if your notation gets messed up, it can cause terrible issues down the road. I mean, there's definitely a temptation to just say, okay, the integral from 0 to 5 of 1 minus x minus 5 is this natural log evaluated from 0 to 5 is the natural log of 0 minus the natural log of 5. Plug it into your calculator, you get an error message. Okay, this integral doesn't exist. And I can't deny that you do end up getting the right answer. But again, we really do want you to be thinking of this as a limit and using this notation and going through the process. All right, this section isn't done. I don't know if we'll finish it on Thursday or not, but we'll proceed with it. I will see you then, bright and early.